Welcome to my Count Anything series, where we will actually train an object detector AI and then learn how to track and count objects. By the end of this, we will have an actual people counting system. But you can use the same process to count cars or animals or anything. I set up for you these notebooks that we can run in the browser so that you can do every part of this even without knowing how to code. So let's get into it. Jump onto your computer, go to my GitHub, and download these 3 notebooks. So first of all, let's explain Google Colab and what notebooks are. So you can go to Google Colab, and this allows you access to this virtual computer where you can connect to a GPU. And in these notebooks, we can run Python code. I want you to really think of this as a virtual computer where we even have a file system. We can upload files here or we can download them as well. Google Colab is free, but one thing to note is that if you move away from your computer for too long, then the runtime will reset and then everything in this virtual computer will be wiped. The way that we're going to be using it, you're going to upload the notebooks that I provide for you, and on the left-hand side, you can see the table of contents in case we get lost, and you can see the file system, all the files that you upload over here. I've written a lot of code for you, and to run them, all you have to do is just press these play buttons one at a time to run each part of the code. And don't forget, at the start of each session, connect to that GPU runtime because we're going to be doing a lot of AI stuff. If you do want to get a little bit of background on Python syntax and Google Colab, you can click on this first link at the top of the first notebook that I provided. And there's things to play around with in there. But basically, all you have to know is just press these little play buttons, and I'll see you in the next video. In this module, let's create a dataset. Basically, what an AI does is it replicates whatever task you show it. In this case, we want the AI to put boxes around the people in our images. So our dataset consists of 2 things, images and the box labels for those images. You've already downloaded these 3 files. Let's go on to Google Colab. So colab.research.google.com, and let's open the first file. We're going to work through this notebook, and by the end, you'll know how a dataset is created. First, let's change the runtime type. So we have a GPU here. For you, I made it easy for you. All you have to do is run each of the cells by pressing this play button. And this cell is first installing a bunch of stuff, downloading a couple of things, and then creating some functions that we'll use later. And on the left, we can see the different sections of this notebook. So basically, we're going to have a bunch of images, and I'm going to show you a couple of different ways that we can label them. Here's an example image with people on it, and these people need to be labeled with bounding boxes. How do we define a bounding box? A bounding box is a rectangle, and a rectangle can be defined by 4 points. We have a special case where the box can never be diagonal. Our AI the format is it's always going to output these either horizontal or vertical boxes, not diagonal. So how many points do we need to define that box? We need only 2, top left and bottom right. Let's run this cell and let's see an example. So I have my picture here, and now I can click on it. I need 2 points to define my box. And there we go, I just created 1 label. So we would need to box every person on this picture. Every box we provide is going to be a positive sample for the AI. And the empty space you can kind of think of as like a negative sample for the AI. That's where a person is not. We've boxed all the people. The boxes look pretty good except for maybe this one and this person. Also notice that there's some people in the background all the way off here. This part, I'll leave it up to your discretion. Do you want your AI to attempt to capture these people, or should we just ignore them as part of the background? So as we were doing our clicks, on the back end, the script was keeping track of the coordinates of those points that you clicked. So how many boxes did we make? A little bit more than 10, it looks like. And here are all those boxes. there are four numbers which represents 2 points. This is the first two is like the XY of the top left corner, and this is the XY of the bottom right corner. So each of the boxes is represented by one row. Let's try to label this image in another way. In my notebook, I'm in the section AI assisted labeling. If you have trouble finding where we are, you can click on the table of contents on the left-hand side. Now, in the beginning of the notebook, we already downloaded a file for our AI. You can see that here when you click on the file system. So this folder icon, you can see this .pth file. This is the AI file. If the file doesn't exist, you can scroll up to the top and see if you ran this cell or not. This is the one that downloads the file. All right, so let's go back to AI assisted labeling. What we're gonna do is we're gonna use this AI model, and hopefully it'll do some of the work for us when we're labeling. This AI model is called Segment Anything. It's made by Facebook. What this model does is that it can find the edges of objects in the screen. So you see when I click on here, it can kind of figure out where the person is. The model doesn't know that this is a person, but it can just basically find the edges, kind of like Photoshop. See how the pixels of this person are colored blue? This is called segmentation. The AI model is predicting the pixel locations of this object. I'm gonna left click to highlight a person, and I'm gonna right click to make that into a box. So we can do that for the people on the screen. This is not perfect, so sometimes you'll have to click multiple times and click around in different points. So I'll do a left click to select a person. That wasn't good. Let's try another one. There, that looks good. All right, so I'm gonna label all the people just like before. So far, to me, it feels like this is taking longer, but it's actually more fun. All right, we have all the people labeled. Now remember that we have the pixel locations of that person, but we can turn those into boxes. So here's all the boxes from those people above. Now let's think about another problem when setting up our data set. Let's say that we're pretty competent at labeling images. We can put bounding boxes around all these people. But where did those images come from? Let's say we set up a camera outside and we set it to take a still image every 5 minutes or so. Then we'll have all these images with people on it. Can you see what the problem with doing that is? Pause the video and think about it for a second. So the problem is, if we set up a stationary camera to take all these images, and that's our data set, then it's gonna have the same background in every single image. The AI model would start to memorize that background image. And basically, if we move the camera even a little bit left or right, then the AI model isn't gonna work properly. So when you're setting up your image data set, you wanna make sure that your images are varied enough that the AI can't kind of cheat. So ideally, you would want to set up a lot of different cameras in different locations and use those pictures. But let's say that we didn't have a big budget and we only had a few cameras. Well, we can do another trick with this segmentation information we have. So now I'm looking at synthetic data augmentation. You can click on the table of contents, this section. So we have the segmentation information from before. Segmentation means like the pixel locations, right? For each of these people, we know the pixels for where they are located. Then let's see on the left side, that's our original image. And on the right side, we just have a random other background image. Are you getting an idea where this is headed? So I can take these people on the left-hand image and place them into this empty background image that I have on the right side. Essentially, I can make two data samples from one sample that I labeled. So check this out. I have all the people from our first image, and now they are kind of just pasted on into this empty background. And we already have the bounding box coordinates for all these people, so we don't have to label it again. You can see on the right side all the boxes. Some of these people don't make sense. Like, why is there a person walking right over a car, and why is there a person up on this telephone pole thing? But this should still be better than having a single background for all your images. I would think of the tier as, if you could have a lot of different locations, that's the ideal one. Then doing this like synthetic image thing. That's like the second best choice. And then the worst choice is all the same background. And finally, we have to format our data in a way that the training program can understand. So click on the last section in the table of contents. Now this thing called COCO. COCO is a data set that's pretty commonly used to train object detection. So putting our data set into this COCO format makes things a lot easier. Basically, imagine that all our coordinates for the boxes and information about which image it refers to has to be stored in a kind of JSON format file. You can see here, this is the format that COCO expects. And for us, this script here will prepare all our bounding box coordinates into that format. And you can see we basically have two images, one a real labeled image and one a synthetic image. And there are a total of 26 annotations. So probably 13 annotations on each image. And the last one, it saves it to a JSON file. If you look in the file system, that JSON file should be here. Great, so we've successfully created this 2-image data set with labels. And we can see, here's the JSON file that we need. Obviously, you're gonna need to do this with a lot more images for your AI to learn something useful. And at the end, you're gonna have a bunch of images, and then you're gonna have this JSON file with the labels. Now you know how to do it. Now we can train your AI. In this module, we're gonna take a data set and then train an object detector. You will actually be training an AI model in this Google Colab. Again, we have our 3 notebooks, so we're on the second one. Let's open Google Colab and drag this into there. Just like before, let's press play on the first few items. What this is doing is it's installing something called Detection. This is the package that we're going to use to train our model. And then we're also going to download a data set. The data set is called Crowd Human over here. And it's going to set up all our files in the right locations. As we learned from the last module, setting up a data set is either really time consuming or expensive. So whenever you can find a publicly available data set that will suit your purpose, it's good to start there. Another thing that happens a lot, let's say that what you wanted to do isn't exactly what the data set provides, but it's similar. For example, this is a crowd human data set with one class of people. But let's say you wanted to do adults and kids as like 2 separate classes. What you could do is you could pre-train a model on the crowd human data set. And then you can take those and fine tune it on a separate data set. Maybe you labeled a certain amount of adults and kids. So wherever possible, you want to make use of public data sets so that you can reduce your costs. Now I want to show you the file system. This is all the data that we have. Crowd Human is the data set, and it unzipped into this Detection folder. Detection, remember that's the package that we're going to use to train. And then in data and COCO, here's all our data, the annotations. Remember from the last module, we made a JSON file. So we have train and validation JSONs, and that corresponds to train and validation. These are our images. So there's a bunch of images in here. I'll explain what train and val are later. You'll notice that this directory is called COCO. This is not the COCO dataset. This is the crowd human dataset. But I formatted everything to look like the COCO format so that by default, a lot of the configurations will work in Detection. Basically, we need to set up the files in a way that Detection can read them. Okay, when we talk about data sets, I really want you to think about the task that you're trying to do and do the images in your data set look like the task that you're trying to do. In our case, we're trying to build a people counter. Let's take a look at some of the images in our crowd human data set. All right, so in this cell, every time you run this, it's just gonna show you a random image. You can see that here's all these people. They label these as masks, but that's not so important for us. Here's another random image. You can see they label people all the way back here. More images of people. Judging by this data set, we should be able to detect people once we train our AI at both a close distance and kind of far away. So you can run this as many times as you want just to get a feel for it, but I think this data set is going to work pretty well. All right, we're about to train this model. What do we need? We need two things. We need our data set. That's what we talked about before, CrowdHuman. And then we need a configuration file that tells Detection what are the parameters that you want to train on. So here we have this directory called configs. And in here, there's all these different folders which represent different architectures. In AI, you start with an architecture. That's the skeleton. Then you keep feeding it a data set, and over time, it learns these weights. For our architecture, we need two things. We need a backbone and a meta architecture. The backbone will be something like a ResNet, which has been trained on image classification. In other words, it has been already pre-trained to do a task like, is this a picture of a human, or is it a picture of a horse or a car or fruits? So this pre-trained AI model can already do that classification. But what it can't do is what the meta architecture does, is propose bounding boxes on a screen. So find multiple different objects on the screen. So the meta architecture, mostly in charge of finding your boxes, and the backbone, mostly in charge of distinguishing between different types of objects. For the meta architecture, there's a lot here, but let's pay attention to two types. Faster RCNN, this is one that you will use when there's more objects, but it's a little bit slower compared to this other one, which is called YOLO. YOLO is faster, but it gets less accurate once you have a lot of objects on screen or large crowds. So in our case, I think we can go with faster RCNN because we might expect 100 or 200 people on screen. Now, once you click on faster RCNN, you see all these different configs. You see this thing called R101, R50. They're talking about ResNet 101, ResNet 50, and they have one more here, ResNet 18. So ResNet, remember, in our case, it's going to come pre-trained, but what are these numbers? So the numbers represent the number of layers. So an AI model, and then like how many layers of calculations do you have to make? I want your intuition to be for ResNet 101 with lots of layers, that's going to be more accurate, but it's going to take more processing time. If we needed something to distinguish very distinctly between classes, then we need more layers. But if we wanted it to run fast, we could use less layers like the ResNet 18. In our case, let's stick with the standard ResNet 50. So that'll be our backbone, and faster RCNN will be our meta architecture. Here, I've already set up a config file for us to use, and let's see what's in here. We can see in here, faster RCNN, that's going to be our meta architecture, and backbone, that's going to be ResNet 50. And it's going to come pre-trained here. This file also contains a whole bunch of other parameters that are going to be used to train. Let's see, what are some notable ones? Here, what is the maximum number of objects that can be on screen? In practice, even if it says 1,000 per image, you're actually only going to get maybe a couple hundred accurate predictions per image. Here we have our classes. We have a single class, which is person. You could have multiple classes like person and car. You could have 100 different classes, which makes the task a little bit harder, which means you might need to use a ResNet 101. This file also specifies like where to look for the data. We set up the locations in that Coco location. And it's going to expect the format to also be like Coco annotation format. And one more thing here, I set it to run for 1 epoch. This. That means that it's going to run through the training data a single time. I did this just so it wouldn't take forever for us to just get a model. But you'll probably get a better model if you train it for something like 10 or 12 epochs. This line of code is what starts our AI training. And basically, we have to specify the config that we're going to use. Right now, what it's doing is it's downloading the pre-trained backbone. Here, you can see that. This training sequence will produce files in this work directory. In here, you can see the date here. This was newly created And once a training cycle finishes, we'll have a checkpoint file in this folder. We can see here that we're on Epic 1 and we are going through the dataset. Like the AI is training on different parts of the dataset, like one batch at a time. We should also see this thing called loss, which should be decreasing roughly over time. The loss is like the error. We have this labeled dataset, right, with all these boxes, and our AI is trying to guess where to place its boxes. And so the loss is basically a measure of like how far off are you from the ground truth labeled boxes. Now you might also have a question, what would happen if I just trained for 100 epochs, like 100 times through the data set? Well, what would happen is that your loss would keep decreasing, like your AI would keep getting better at the training data set, but it would start to do this thing called overfitting, which is basically like it would start to memorize the images in the training data set. In other words, whenever it sees this specific image, okay, I know exactly where to place those boxes. But we don't want that. We want the AI to perform well in situations it hasn't seen yet. So in other words, generalize what the objects are supposed to look like. That's why we have this thing called the validation set. So the training set, that's what we use to train the model. The validation set, the AI never gets to see that validation set. So as we go through all these training cycles, we should also see the validation loss going down over time until it hits a point and starts to go up. Once the validation loss starts to go up, that gives us an indication that AI might be starting to overfit. Now we can see here the ETA is roughly 1 hour. So in 1 hour, we will have our AI model. Okay, we're back. Now you should see this file in your work directory called Epic1 path. This is your checkpoint file. This contains all the numerical values for the AI to do its object detection. In other words, this is all the meat that's needed for your AI. In your notebook, you can click on table of contents and then go to running inference with your model. We'll run this cell which loads up our model. And now let's take a look at an image that we have. Nice, we have this image with a ton of people on it. Let's see how well our AI does. An AI that we trained for 1 hour. Let's see what's gonna happen. Nice, so this is pretty cool. The AI model got a lot of people pretty good. Like look at this box on this person and this one on this person. The AI also missed a lot of people as well, like this crowd of people here, a few individuals up here and on the left side. The model will get better if you train it for longer, but it's still gonna have some problem areas. Like the crowd will still be difficult, I think. But think about what we just did. We trained an AI model in this virtual notebook and it's doing something relatively smart. And lastly, let's just run this last cell. It kind of prints out like what is the information that's coming out when you run your AI model. So you can see it has these boxes. That's the coordinates for the bounding boxes. And if we scroll down, it has something called labels. This is if you have different classes that your object detector can detect. In our case, we just have one class, which is person. So everything is just a 0. And scores, this is how confident is your AI in its detection. That's it. We've just trained an AI and we've run an image through that AI. Cool. This is the last module. So far, we've built an AI object detector. And by the end of this module, we would have built a full people counting system. So let's use the third notebook here. And we'll open it up in Colab. Okay, we're in our notebook. Don't forget to change the runtime type to GPU. For those that are wondering, what are these different types? A100 is the fastest, T4 is the free one. We're gonna run this cell that installs some dependencies and also MM detection. MM detection is what we use to train our AI model. After that, we're gonna run this cell, which is gonna download 3 files, these 3 files. The first is the config that we use to train our AI model. It's also going to be used to recreate that same AI model in this notebook. Then along with that is the checkpoint file, which contains the numerical values for our AI model. And third is a video file, which we will run our people counter on. Nice, we can see on the left-hand side in the file system, here's the 3 files that we just downloaded. Make sure to run this cell, hidden functions. It contains a bunch of helper functions. I hid them, but you can take a look at them if you want to. Now this next cell is just going to help us to visualize videos inside of this notebook. This video is of Shinjuku, Japan. You can see there's a ton of people on screen, which is good. I have another script here which just grabs a few random images from that video file. Take a look at these images. There are 4 images here. And why did I take that? Because I want to run my detector on them. Now let's load up our detector. We need those 2 files, the config file and the checkpoint file. Our model is loaded up in this notebook. Now let's run the detections. Here's those images that we got from the video, and here's all the boxes. I want you to get a feel for when our model is capable and when our model is kind of having a hard time. So you can see these people way off in the background and in a big crowd, they're harder to get. Also notice again, all these people up here on this crosswalk, we got almost none of them. You may also notice that at the sides of the images, there's a little bit of a camera distortion. This distortion makes it hard because most of our images in the dataset most likely don't have this kind of distortion. That's why we're missing some people at the edge of the images. See these couple people here, and see there's a couple people on this left side too. What about in this intersection up close? We're getting most of the people. These few people that we missed here, there's not a good reason why we missed them, because they're not distorted, they're not in a big crowd, and they seem to look like everybody else. My guess is that the AI is reaching an upper limit of how many objects it can detect on screen. What we could do is we could cut off the left side of the image, which forces all the detections to be placed in this area, and we might be able to get some of these people. So those are all the cases where we're missing people. What are the cases when we're detecting extra people? There's this detection here where there's nobody, and there's this detection on the traffic light. Eventually what we'll do is we'll draw a line on our screen, and then we'll count people walking across that line. So this empty space up here, at the traffic light, those two won't be a problem. But this guy on a motorbike will have to think of something. So far, these boxes on screen, these are all drawn by detection internally, but we need access to the boxes so we can do our own calculations like tracking later. So this next part, let's take a look at how to do that. If you got lost as where we are, you can click on the left side and manually manipulating detector results. First thing, let's just print out what our results look like when it goes through the detector. We get scores, that's how confident the AI is. We get classes, we're only detecting one class, which is people, so it's all zeros. And then we get the boxes. This first box corresponds to this first confidence score. The second box corresponds to the second confidence score, and so on. So that's kind of how it's laid out. So let's visualize all the boxes on our own. We're going to print out all the boxes that the detector gives us. You can see that there's a few more boxes here. Like look at this big one up here. That wasn't there before. And there's this guy that's double boxed. I don't think that happened before. An easy way to filter out some of these boxes, and probably what detection was doing behind the scenes, is that we can use the score. For example, we can say only show me the boxes above a score of 0.3. Let's see what that looks like. And just like that, we got rid of this big one up here, and we got rid of that double box that was on this person. So adjusting this score threshold, you're going to have to try a few different values on a few different images and get a feel for the balance for what's too high and what's too low. For example, let's just try and put 0.99. So a really high threshold. Now we get almost no one. And if we put the score down to 0, basically the scores have to be between 0 and 1. If we put the score down to 0, now we have a lot of those false detections again. So somewhere in the middle, try out a few values and see what works for you. There are other ways to filter your detections besides just that score. For example, the size of the box. Is it too big or is it too small? In this case, you could also use a height to width ratio. You notice that most of our boxes are vertical. So some that are more squarish or even horizontal, those are probably going to be false. So we have the detections, and then we get the boxes, and then we filter out some of the noisy boxes. Now let's move on to tracking. In order to count the people that have walked through this scene, we need to track them. And what tracking means is from one frame to the next frame, can we keep track of who is the same person? Here are the first 2 frames of the video. Here's the first frame, and down below, here's the second frame. This video happens to be running at 10 frames per second. And most of the time, videos run at 30 frames per second, but we're dealing with 10 here. So if you do the calculation, that means 0.1 seconds has passed in between this frame and this frame. Now let's look at a couple of people. How about these 2 people on the side? We look at them here, and then we look at them here. Almost no difference. I'm just gonna superimpose those 2 images over each other just so you can get a feel. This blur is basically how much this person on a bike moved. Now what about the boxes? Let's think about how far the boxes have moved. Here we see the green boxes are the first frame, and then the blue boxes are the second frame. You can see that here's the green box below and then the blue box on top. That's how far this person has moved. Same here, green box and then blue box. So that's what we're going to use as our method of tracking. If the boxes are overlapping, we're going to say that is the same person. Now what about these 2 people here? Their boxes are overlapping with the previous frame, but they're also overlapping with each other's previous boxes. So let's modify our tracking to go like this. We're going to choose the box that overlaps the most, and then that's going to be the same person. There's a pretty common calculation that goes like this: intersection over union. It's the intersection area divided by the union area. And it's going to give you a value between 0 and 1, 1 being exactly matching boxes and 0 meaning completely not overlapping boxes. So I want you to choose a person. You can choose any person on screen. And then we're going to see in video what the tracking looks like. If you're interested in picking apart the code, here's a section of code that just opens up the video. Here, we open up the video, and in this while loop, so a while loop is something that you're going to do over and over again. So we're going to keep reading an image over and over again from the video, and then down here you can do some calculation. This is just a basic open the video and then read it. And here in this part of the code, it does the same thing. You're going to open up a video, you're going to have a while loop which keeps reading an image, and then you'll do some calculations with IOU. Okay, so let's take a look at that guy we chose. Here, it's tracking him pretty good. And if you want to do it again, you can choose whoever you want and then run this portion of the code again. Let's take a look at this other person we chose. And you can see, oh, we missed him in between. That's a good segue into our next problem. See, we have a lot of these weird cases. For example, if we're tracking a person and our object detector, which we know is not perfect, what if we miss a detection in between? Then the tracker is going to miss tracking him. We can solve that by letting the box stay around even if it doesn't match to a box on the current frame. So we'll just leave the box there. Then on the next frame, if there's an overlap, then we can match him onto that one. Okay, but then we'll have another problem. If we do this strategy where we leave boxes around even when they don't match, then over time, we're going to have all these boxes collected all over the screen. And we can solve that by letting the boxes stick around, but we're going to delete them if they stick around for a certain number of frames. What about another weird scenario? What if a person walks to the edge of the screen and another person walks onto the screen at the same time and takes his box? So there's these little scenarios that you have to think through, and depending on your use case, you might solve them in different ways. Now here I have some code that does some of these things, and we're going to put trackers on everybody. One thing that's pretty cool about running these cells is that you can see this little arrow that shows you where in the code it's processing. you can see that it keeps going through this while loop over and over again. It's running the inference, that's the detector, and then it's doing a tracking step, and then it's creating a video file out of it. Here we're tracking everybody. Everybody has their own color. Everybody is supposed to maintain only one color. There's a couple mishaps here and there. Now here's the last part. If we can track everybody, now we can count them. So we're gonna have to draw a boundary on screen, and that's gonna represent our counting line. A line segment is made out of 2 points, so you can draw 2 points wherever you want to count people. If you draw it like this, it's going to count people that cross up and down here. You might have a use case where you'll have more than one boundary. For example, what if you needed 2 lines? Then you can count people crossing each line, like that. This will be useful, for example, if you're counting cars on a highway and you want to keep track of each individual lane. But for now, let's just go with one line for simplicity. You can see those 2 points that we just clicked, here and here. These are the points from those clicks. We can do counting like this. We have a line segment from the tracked person, and we also have a line segment from this boundary we just drew. And whenever those two intersect, we know that the person has crossed the line. Here's a script that does that. And let's create a video file. It's going through the while loop over and over again. Here it runs the inference, then it runs the tracking, and then it runs the counting. One last thing it's going to do is it's going to display the counts on screen so we can see them. Running the inference, then running the tracker. We can start to see a lot of time is spent on the inference. Actually, running the detector takes the most amount of time out of all these things. Here I set it so that their box turns black whenever somebody crosses the line. And can we see those counts? Here's the counts in the corner. I just ran this on a small portion of the video. If you want to run the whole video, just change this max frames value into something really big, like 100,000 or something like that. And one more thing to note, we loaded up a video file here. If you want to change this to, let's say, your USB camera, all you would have to do is insert that here, and the rest of the algorithm stays the same. And that's it. We've learned how to create a dataset. Then take that dataset, turn it into an AI model. Take that AI model and turn it into this people counting system. We've done everything, and the code's all there so you can play around with it. Have fun.